Alright, hello. In this video, we're going to be going over problem set 5 and the walkthrough for each question. So let's start with question 1. Compound A is analyzed both for its elemental composition and its mass spec. It has a percent composition of 91.23% carbon and 8.77% hydrogen. The mass spectrum shows a molecular ion peak at 92 mass to charge ratio. And basically it's asking us to calculate the molecular formula for compound A. So since we're working with compound A, we're given the percent compositions of the atoms as well as the molecular ion peak, so we kind of have two approaches to how to find the molecular formula, which is very nice. So let's start with option 1, which is using the percentages. So remember, if you guys watch my problem set 4 video, I'll put a link to that video right here. I kind of go over how to find the molecular formula as well as empirical formula, and this is another good way application of the little jingle that I did mention. So right here we have, if you guys remember, the jingle goes percent to mass, mass to moles, divide by small, multiply till whole. So basically all that tells you is we're given a percent. So let's start with carbon, 91.23%. Percent to mass. Since we're given percentages and we're not given a mass, we are given a mass of 92, we can kind of just go and assume that it's 100. So percent to mass, we can just assume this as a 1-to-1 ratio as 91.23 grams of carbon. Same thing with hydrogen. 8.77 grams of hydrogen. Percent to mass, the next part of the jingle is mass to moles. So we're going to divide by the mass on the periodic table, grams of carbon, grams of hydrogen. And that is going to give us 7.596 and 8.683 moles respectively. The next part of the jingle is we have percent to mass, mass to moles, divide by small. So basically the divide by small portion, we're going to take these 2 moles and divide by the smallest one, and in this case it's going to be 7.596. And that's going to give us a number up here of 1 mole of carbon and 1.143 moles of hydrogen. So we got percent to mass, mass to moles, divide by small, and the last step is multiply till whole. So this method, I like to do the guess and check method. For this one, it is kind of annoying because you might have to guess and check for a while, but once you do the math out, you find that they both have a common number of 7. So when you multiply this, you'll get 7 moles of carbon, and this one turns into 8 moles of hydrogens. So now we're given the formula of C7H8. Alright, so that's what we have so far, and let's say, for example, you're not confident that this is the right answer. Remember, we're also given a mass to charge ratio of 92. So we can use that as a second route using the rule of 13s. Whether it be given spelled out like this as 92 mass to charge ratio, or given on an actual chart mass spec, you can find the mass to charge ratio, and once you know that, you can deduce the molecular formula. So in this case we have a 92, and the rules of 13 basically says you take the mass to charge molecular ion peak divided by 13, and in this case we're going to get a decimal number. If we do that out, it's going to be like 7.0769 or something like that, but we want to look at this whole number here. That's going to tell you the number of carbons. So we can have C7, but we don't know the number of hydrogens, and the next step is to take this whole number, 7, and we're going to multiply it back by 13. So if we get 7 times 13, I'm going to draw a line here, 7 times 13 is going to give us 91. And now we're given 91, and if we compare that to the original mass to charge ratio, 91, 92, it's going to be a one number discrepancy. So if we subtract that, we should just get 1. And basically that 1 is going to be added on this 7, if that makes sense. So it's going to be 1 plus 7, which is the original whole value number we solved for up here. And this is going to give us C7H8. This is kind of confusing the way I'm wording it. I apologize for that. I feel like the best way to get used to using the rule of 13 is just by applying it, doing as many practice problems as you can, and kind of checking your answer to make sure you're on the right track. But since we got C7H8 for both of the methods, we can probably assume that this is the correct answer. Next question. What is the degree of unsaturation for compound A? Is it likely that compound A is aromatic? So basically this goes back to, do you know your formulas? C7H8, degrees of unsaturation, is going to be number of carbons minus 1/2 the number of hydrogens plus 1. And since we're just working with hydrocarbons, we do not need to worry about nitrogens or halogens or anything like that. And this should give us a degree of unsaturation of 4. And is it aromatic? Basically, if you guys remember, degrees of unsaturation just basically means how many double bonds or how many pi bonds you have and how many rings you have. It can be a mix and match combination of whichever. So in this case, degrees of unsaturation of 4, it's asking us, is it likely that this compound is aromatic? So it's kind of hard to say for sure. But in this case, we're going to say, for our purposes, yes, it is likely to be aromatic. Because in this case, benzenes, remember, have a ring. That's going to be 1 degree of unsaturation and 3 of these pi bonds, which is going to be a total of 4 degrees of unsaturation. It could maybe be something where you have like 4 different pi bonds in a straight linear chain or something like that. But it's unlikely for it to be like that, and for our sake, we're going to say that if you have a degree of unsaturation of 4 or greater, there's going to be some aromaticity in here somewhere. Okay, so now we're given question 3. IR peaks are observed for compound A at 692 and 725, in addition to a variety of peaks to the immediate left and right of 3000. Draw the skeletal structure for compound A. Right, so we're given a lot of information here, but remember, we're still working with compound A. So in this case, we know that compound A has to have a molecular formula of C7H8, as well as degrees of unsaturation of 4. And as we said in question 2, is it likely to be aromatic? It is likely to be aromatic. So we can kind of already check off that the fact that there's probably going to be a benzene somewhere in here. So if we have a benzene structure that already checks off 6 of our carbons and 6 of our hydrogens. But remember that there's going to be another carbon not accounted for, and the most logical way to go about this is to add a methyl group here. And I kind of just did this all without even knowing, or not all without even using the information given by the IR peaks. I kind of just used it, deduced the structure based on questions 1 and 2. So I'm not saying that you guys should do this. It's just kind of a starting point. Like, where do you want to start off here? And then using additional information, you try to piece together this puzzle that is unknown. So in this case, we have peaks immediately to the left and right of 3000. So if we look here, or I guess compound A isn't given, but it is known that if we have peaks directly to the left of 3000, that is a pretty clear indication of some sp2 hybridized carbons, and that is going to be very, very prevalent in benzene structure. So it's likely that there's a benzene here, as well as the peaks being observed at 692 and 725 indicate that is likely monosubstituted, being this coming off of here. And I believe you guys are going to be given the different substitutions for para and mono and that kind of stuff. So I wouldn't stress about memorizing each individual peak like location, but just know how to use the chart and how to interpret the graph when you're given it. Okay, let's move on to question 4. Continuing from above, remember to read the question carefully. Continuing from above, compound A. A lot of students didn't know where to kind of go from here, but if you just read the question, continue from above, compound A, we're given this whole structure here, right? So that's kind of what we want to go with. Is reacted with H2CrO4 and yields compound B. All right, so now we're kind of trying to combine everything we've learned from organic 1 and organic 2. Once we're given a structure deduced by IR, we can react that with certain reagents. So it's very important to know your reagents, know your reactions, know your exceptions. So in this case, it's being reacted to H2CrO4, and this is going to oxidize, if you guys remember, it's going to oxidize this group coming off the benzene, more specifically the hydrogens coming off of this carbon. So it's going to turn this into a carboxylic acid group. Remember that this, in this case, only works because you have hydrogens here. If hydrogens were to be absent, this reaction would not occur. Right, so this is our answer for question B. So now it's asking, what is the mass to charge ratio, what mass to charge ratio is expected for the molecular ion of compound B? So now we're given the structure of compound B, and mass to charge ratio is just a fancy way that the machine tells us what is the molecular weight of the compound. So we're kind of just counting atoms here. So we have 1, 2, 3, 4, 5, 6, 7 carbons. We have 1, 2 oxygens. And for hydrogens, we have 1 here, 2, 3, 4, 5, 6. There is not going to be a hydrogen here. So we're given a molecular formula of C7H6O2. And this is kind of just using the periodic table, and we're going to find a mass to charge ratio probably of 122. So now let's look at the final questions, set of questions. For each of the following, use the provided IR spectra to determine the functional group present and whether or not the molecule is aromatic. There is only one functional group per compound, which makes this a lot more easy and not much of a headache. So starting off with compound C, I would say the first thing I would look at when examining IR, look for any immediate red flags. And when I say red flags, I don't mean like a toxic boyfriend or girlfriend. I just mean what jumps out at you immediately. So in this case, what is screaming at me is compound C. Boom, peak at 1716, around that 1720 mark. So what does that tell you? It tells you you likely have a C double bond O somewhere in your molecule. Dr. Santos in class, as well as in the notes, provided a flowchart for deducing functional groups, and I would live and die by that flowchart. That is very helpful. It is going to help you out in a lot of different situations. So we have a C double bond O here. We don't really have any major C single bond O peaks here, so we can eliminate several functional groups with that. If we look over here, we don't have a big ugly peak at 3300, and we don't have any groups poking out on the left of 3000. So it's likely that there is no sp2 hybridized carbons, so it's probably not going to be aromatic. And obviously we have the sp3 carbon hydrogen stretch, so we can likely deduce that this is going to be a ketone. And is it aromatic? We don't have any peaks on the left of 3000, so nope, not likely to be aromatic. Okay, next question here. Compound D, immediately, what jumps out at you? What is the red flag? For me, the red flag is this alcohol stretch here. That'll tell you that you're either working with an alcohol or a carboxylic acid. And if you remember what the carboxylic acid functional group looks like, it looks something like this. So we have the alcohol group here, and we also need to have the carbonyl group for it to be a carboxylic acid. Do we have that C double bond O stretch here at 1720 or something like that? I don't see anything right there. So it is likely that OH is going to be your only functional group, and as stated previously, there's only one functional group, so we can automatically say that this is an alcohol. And is it aromatic? Do we have any major peaks to the left of 3000? I don't see any. No overtones, not really that much out of plane bending as well, so not aromatic. Okay, lastly, we have compound E. I guess not lastly, but compound E. Immediately, what jumps out at me is this nasty massive C double bond O. So we're likely to be working with a ketone or aldehyde or whatever it may be. So next up, do we have a C single bond O stretch? What else jumps at me? I would say this peak right here at 1277 jumps out at me pretty intensely, and this is indicative of a C single bond O stretch. So we know that they have a C double bond O stretch and a C single bond O stretch. So automatically, I can kind of already assume we have something that looks like this. And if you remember what functional group this is, it is an ester. An ester functional group. So you could argue that maybe there is a C single bond O somewhere else in the molecule and a C double bond O somewhere else separately, but generally when you're dealing with IR, there's a saying, I might have said it before, but when you hear hooves, you want to think horses, not zebras. Basically, don't try to overcomplicate it. Think of what is most likely to be the molecule that you're working with. Try not to think of anything too extravagant. It's likely going to be a lot more simple than you might think it may be, because these spectra sometimes do get confusing. So we likely assume that this is an ester. And is it aromatic? So let's take a look here. In this case, I'm kind of seeing a little bit of overtones here, although not that strong. There is some out of plane bending over here, as well as to the left of 3000. For the first time, we see some peaks at the sp2 carbon range. So that kind of tells us that it is likely going to be aromatic. So last question is question F. Aromatic substitution pattern. Is it monosubstituted, ortho, meta, or para disubstituted? So remember, you'll be given a chart, so this is going to be less of a headache. So it's not asking you for whatever functional group it may be or like that kind of stuff. It's just asking, is it para, di, mono? What's the substitution pattern here? So in this case, we have a peak jumping out at 814, and if we look at the chart, that is likely going to be a para substituted benzene. All right, this is a lot of information here in problem set 5, because it does cover a lot of mass spec stuff, a lot of degrees of saturation, and now we realize that we can combine that with the reactions from before. So definitely brush up on this after spring break and before the exam, because it'll definitely come back in exam 3 as well as the final exam. Thank you guys.